Section 2.1, just finishing off the class notes today, examples 9 and 10. We had almost finished example 9. We had looked at the function and discovered that if we factored it, there was a common factor that cancelled very nicely, and then we could find the limit by substitution. So at this point, we're left with the function was y equals x plus 2, but x could not equal 2. Remember, we're taking the limit as x goes to 2, but we don't actually care what happens at x equals 2. So the fact that there is a hole there doesn't matter. And so to get the value of the limit, we're going to substitute in the simplified function, and we get 2. We substitute here into x plus 2. We get 2 plus 2, and the limit is 4, and that's what we found graphically. So to summarize what we did here, the algebraic technique that I refer to as algebraic cunning is a very common way of doing these limits is to factor, cancel common factors, and then substitute. So you'll have some homework once to practice doing this. Example 10 requires a different kind of algebraic technique. Hopefully when you look at example 10, it'll remind you of some sorts of problems that you did in pre-calculus. I think you came across this when you was actually doing trig identities, something a little bit like this. I want the limit of this. If I substitute straight away, x is 0, I get root 1 minus 1 over 0, and alas, that's going to give me 0 over 0, which doesn't exist. Remember that this doesn't mean that the limit doesn't exist, it just means that substitution doesn't work. So what we can do though is we rewrite. I have the limit as x goes to 0, root x plus 1. My pen's giving me a bit of trouble today. Minus 1 over x. And what we do is we're going to multiply numerator and denominator by the same thing. We're allowed to do that. And what we choose to multiply numerator and denominator by is something called the radical conjugate. So let me write that down. Multiply numerator and denominator, hope you can read this, by the conjugate. You came across the concept of a conjugate with complex numbers. Radical expressions also have got conjugates. So if I make a little chart here, I've got an expression and then its conjugate. And I mean the radical conjugate. I just don't have room to write that. So if I have 3 plus root 7, the radical conjugate is 3 minus root 7. If I have root 5 minus 6, the radical conjugate is root 5 plus 6. Okay, so let's multiply. The radical conjugate here is going to be my root x plus 1. Don't change what's under the radical sign. Plus 1. Root x plus 1 plus 1. You're allowed to do this because it's effectively multiplying by 1. You multiply numerator and denominator by the same thing. Now, when we simplify, we're going to FOIL out the numerator. All right. Root x plus 1 times root x plus 1 is going to give me x plus 1. And then when I do the outer and the inner terms, right, the outer and the inner, I've got positive root x plus 1 and then minus root x plus 1. Those two cancel to give me 0. And then when I do the last terms, I'm going to get negative 1 times positive 1, which is negative 1. Should use parentheses, although I would have gotten away with it if I had left them out, because x plus 1, there's no sign in front of it. Now, the denominator, I'm going to leave. I'm not going to try and distribute, because in terms of strategy, that's usually not the best strategy. When you multiply out, just really only multiply the conjugates, and I'll explain why in just a minute. Now, when we simplify this, we get what? The numerator is x plus 1 minus 1, that's just x. The denominator, remember, we're going to keep that, don't bother to distribute. And we find, whoop-de-doo, that we have got a common factor in the numerator and denominator that we can cancel. So let's do that. X into x goes once, numerator and denominator. And then what we've now got is an equivalent function. We've lost the information. By cancelling the x's, we've lost the information that x can't be 0, but that's okay. That just means that's where the whole would be in this function. And so now I'm going to substitute. And when I substitute x is 0, I've got 1 over the square root of 0 plus 1, and then plus 1. And all that turns out to be 1 over 2, and that is my limit. Notice I use the limit notation all the time until I actually do my substitution and find the actual limit, and then I don't write the limit as x goes to, because I'm actually now finding what that limit is. All right. Just a quick note on adding to the notes. We've got here that we multiplied numerator and denominator by the conjugate, and then let's just add, after we've done that, all right, we're going to multiply the conjugates. I'm sorry, this is hard to read. My pen is giving a lot of trouble. Multiply the conjugate. So 1, 2, multiply the conjugates. And cancel. Hopefully you'll find a term that you can cancel, and then you can do substitute. And to get back to the strategy, let's just add that very quickly. Strategy. Don't multiply. It's on the denominator. Actually, don't distribute. This. Only multiply the conjugates. Can you think why? Well, the reason is, if you distribute the x, you will then have to factor it back out in order to find the common factor to cancel. So it's just a complete waste of time. It's not a mistake, it's just a waste of time. So that's why it comes under the best strategy heading, and that's it. I hope you watch this on iTunes, because you can speed it up, and we're done.